Hi, I'm Andrew Lowell, and welcome to FX PhD's Particle Fundamentals and Fuzzy Logic. So this was a super exciting course for me, and the reason is because it really dives deep into one of the most basic and yet complex aspects of all of effects, and that's the particle. So, by my thinking, if we can make a shark feeding frenzy with just simple particle attributes, and here I'll show you the flipbook render. So all of these motions and velocities, accelerations, decision making, target seeking behavior, we can see the red dots as the targets. All of that doesn't use any fancy tricks or anything. It just uses pure particle attributes. And so this course will allow us to dive really deep into the types of things that really keep people from progressing into the really exciting things that geometry, logic, and Houdini attributes in combined with simulation and feedback are really capable of, like rotational math, like velocities and feedback, and just like natural variation, noise, random, etc. So this course is really designed for that, and I couldn't think of a better example to showcase those things than such a complex motion as a shark, a bunch of sharks interested in their subject matter. If you look in the class files reference folder, I've included a URL of a shark feeding frenzy. It's really important to base all your decisions that you're going to make aesthetically off of reference. I've always loved sharks, but I learned quite a few things by studying the reference that I didn't know in my head already. So as you progress into the latter lessons and you make your own decisions based on how they swim, how they turn, etc., then I encourage you guys not to just to copy the values that I set, but actually to try to really learn the flow and set your own values and come to the same conclusions or better conclusions than I have. Okay, so this is really good footage, and there's plenty more online. We have a model of a black-tipped reef shark, and I've already set it to scale. So let me give you a quick walkthrough of the final scene. And then in the first lesson today, we're really going to break down two really core aspects of what we need to know to go forward. One aspect is velocity and how to add to and seek in velocity. And the second notion is a timer and how to create those things in a simulation paradigm. Let's do a walkthrough of this scene. So I have a few things in here for dramatic effect. We can generally ignore those. I have a static camera and animated cameras if it's underwater, a few ROPs, an ocean floor, and a few things to showcase the scene, such as merging the targets over, as well as an ocean surface. And then we are going to use the ocean surface later on to get a little current going into the noise of these sharks. Okay, but the most important thing, the thing we're going to really work on is just the shark particles. Within this scene, even though it looks like there's a lot of stuff going on here, and there is in my shark rig, I'm basing the shark rig off wire deformations. This is beyond the scope of the class, so we're not going to cover the actual wire deformation process beyond the pulses in the particle that make it swim left side, right side. So all of this is in here, and we can use it purely as a visualization mechanism of our particle logic. So I've got on this deform, the output, I've got three modes. I've got a smooth deform, which takes a long time. It's very pretty. A fast deform with a lower res shark, and the rigid, which is what I have on right now, so that we can see some particle playback. Okay, so up here in the scene, this is all just going to be used for testing and various distribution of the shark. So there's one shark or different targets, different scenarios like that. I have a source and the targets, and these guys should always be the same number of points. Here we have the ocean surface that I'm not going to use till later. Okay, but the real action is going to be in the particle network, and there's really no actual particle nodes in here. It's all made of VOPs and we're just going to do all of our decision making, which can be quite complex. For instance, there's circle behavior that causes these sharks to circle around their prey as opposed to actually go to its prey and stop. So that's all in here. We'll get to that in the latter classes. We're going to get to this guy pretty quickly, and this is the swim pulsing that causes the shark to accelerate and decelerate according to its fin motion. There's an up vector and a normal that causes the shark to be orientated correctly. And then there's 3 axes that we're going to get into, basically one lesson per axis. There's the left and right direction, or the overall direction toward its prey. Then there's if it swims upwards or downwards, that's a separate node. Okay. And then finally, there's the tilt of the shark. We're going to add in some forces and also do some banking. And then it's going to get really interesting as we dive back into the pulsing and the swim behavior to really give it the final touches, meaning if it goes too fast, it's just going to stop swimming and glide. It's not going to be perpetually swimming, and it's going to maybe circle around its prey. Okay, so there's quite a bit of stuff in here. Oh, and one more thing is that sharks don't go as fast sideways as they do forward and backward, or just forward. So here I've got some air resistance, which is actually water resistance, and we'll calculate that as well based on the angle that the shark is swimming to make it bank properly and maneuver through the water. Okay, so yeah, we're going to make our own big complex particle simulation from scratch. We're going to use lots of fuzzy curves or lookup curves and VOPs in order to accomplish our objectives. So let's get started with 2 of the main concepts. And the first one is just going to be understanding really what a particle is and does and how velocity is applied. Okay, so I'm going to start off with a few little tips I have for working with very deep particle systems. So one of the first ones is we're not actually going to be doing our work inside of here as far as our attributes and whatnot, because we have to dive in here and then we have to dive in here. Okay, so instead of that, it's much easier if we just select this view in SOPs and viewing that in SOPs. Okay, and I'm just going to lock this so we always have the particles coming directly out of that. Okay, and let's just make our own particles for the first lesson here, because we're going to be taking a fairly abstract first start. Okay. These are our particles. Okay, let's start at frame 1. Okay. And so I'm going to click on this and let's get our attributes all up. And then I'm going to lock that. And also I'm going to lock this view. There we go. Now we can view the rigid sharks, but in this case, I'm not going to. I'm just going to view this as well as the targets that they're seeking. So I'm going to control click here, and now I've got the targets. So I'm going to see in very quick playback what these guys are doing. So all of those systems put together, they're just flying, because this is really just pure vector math that these VOPs are doing for us. So we can see the particles are seeking out these black dots are the targets, and they're adapting their behavior based on where they find these black targets. So let's keep things simple, and let's start off with just one source and one target. So I'm going to go all the way up to the start of the system, and this is where I'm setting the count of the sharks. So I'm just going to set the divisions to 1. All right. Now I'm just going to visualize the container, and we don't really want noise on the target here. It can be confusing as we're getting our system to work, so I'm just going to bypass that. So now we should just be left with a single particle that is tracking its non-moving target. Okay, and there's a lot of stuff that's going on in here. A lot of attributes. Let's just start in the same way that a basic popnet would be started off. So I'm going to go in here and I'm just going to delete everything, and we should just be left with the basic popnet. Okay. So it's not doing anything now. All right. And maybe reset the simulation. Okay. So now let's just make this particle go in the direction of the target. So I'm going to drop down a pop-fop. And this is just data, so that's why this wire is purple. Okay, so what we could do is we could just add to the position in the direction of this target. First, let's get the actual position of the target. So that isn't really accessible here. We have to find it up in SOPs. So how do we do that? Well, we need to load it from this file reference. So I'm going to make a new parameter, target points. It's going to be a file string, and we're going to load in the position. In this case, we want to have the same number of targets as sharks, so I'm just going to use the current point number. Okay. And so now we have to actually target that to the position. So this would be going into the input number 2. So that would look something like backtick, because it's an expression, op input path of the parent, which is particles 1. So that is dot for itself, dot for the parent, and then input into the particles 1 system 1, and that should evaluate to our targets. And now we need to have that in memory, so I'm going to use the op syntax to load that in just like a file on disk. Okay, and we can test that out, and let's see if it is successful. And let's just put this guy into the new position, and it did work. Okay, cool. So now I want to figure out how to make it go gradually in this direction. So for that, I have the position here and I have the current position. So what we do anytime we want to orient a vector in the direction of another vector, we would subtract. And we're going to do these kind of operations so much over the next few classes that this is just going to be instinctual by the end of it. At least that's the idea. Okay, so we've got a subtraction here, and let's just preview that into normal to see if that's working. And it's going the wrong way, and my normal is 0.2, so we want to scale that up. Okay, so to get it to go the right way, I'm just going to reverse the inputs. All right, so that's successful. And this vector right here, I see this as a really valuable vector that we wouldn't really want to change too often. So in this case, I don't want it to be a normal. I want it to be a vector that we're going to use over and over again in various systems. So for that, I would probably export that as an attribute. So using a parameter or a bind, I'm just going to say target vec. It's going to be a vector, and we'll export when input is connected, and it's going to be invisible to our VOP interface. All right, so now we have target vec. Okay. So we can just kind of leave this guy here. Okay. And once it's computed once, we never have to do it again. And that's really the value of saving it out as an attribute. The rest of the way is that we don't have to gather it over and over for different systems. Okay, so now I want to move this particle gradually in this direction. How do we do that? Well, there's the simplistic way, which is to just move the position a little more each time. So using another VOP, I'm going to get the target vector. Okay, so here's our target vector. Oops. And here's our current position. So if we wanted to, we could normalize the target vector, meaning make it a unit length. Let's come up with a visualizer for target vec. I might already have one. Yeah, I do. Okay. Okay, so here's the target vec. This is how long it is by default. It's just this to exactly that. And by normalizing it, we're making it a unit length. So it's going to be either a little longer or shorter. This is always going to equal 1. Okay. And what we could do is we could add this amount to the position. So I'm going to multiply this vector by the increment of our choice. So let's say we want to multiply that by move. And let's export this as test, because I don't really want to change the target vector. Okay, so that's going to be test A, actually. Okay, so whatever we multiply this move by, it's going to be that length. So here it's really tiny. Okay, a little larger. And the idea is we're going to add that to the position each frame. In a simulation, the previous frame is going to show up in the current set of attributes, whether it's a target vector or whether it's position, because the idea is with particles is we're doing this over and over and over again. It's not just going through here once. Once it's solved, it's going to go here the next frame and the next frame. So now let's see if it's actually working. And it goes and it moves and then it stops. If we moved it much slower, see, it's moving much slower now. And it's adapting to the position. Now, the problem with using position is that it fails to interact with the environment. We can't really do, it's not in motion unless we're actually just, it's like picking it up with our hand and just placing it somewhere else, and then picking it up with our hand and placing it somewhere else. So position doesn't allow for all the neat tricks that pops can do, like collisions or like noise fields or all the great things that you already have access to in dynamics and in pops right here. So we really don't want to just hard code the position. What we want to do is actually use velocity. So that would not be here, that would be here. We'd be adding a certain amount to our velocity on every frame and then spitting that out into the velocity. So if we do this now, it's probably going to be quite a bit faster, but it's going to have a slow start, and it's going to keep accelerating and accelerating and accelerating as it gets closer, and then it's going to overshoot, and it's going to take it a long time to adapt. We're also going to have curving behavior here. Okay, so all particles work best in seconds because we could do oversampling, we could have subs, like a higher frame rates, lower frame rates. We don't want to change the entire particle system. So for that, if those changes occur, we want to multiply all of our forces. In this case, this is kind of acting like a force. We want to multiply that by the time increment. So I'm going to take the move amount and multiply that by the time increment. And we need a much more pronounced move amount. Let's say 1. Okay, and now if we subsampled it, if we change our frame rate, these values wouldn't actually change. So there it's curving to adapt. Let's increase that a bit. There we go. And notice how much it's overshooting. So now we could follow that up with some pop drag. So now it should adapt a little more organically. There we go. And there you have it. So velocity would be, if you're just manipulating the velocity attribute, then the solver is what's causing the position to move. And this would adapt to our forces, our collisions, all that. So that's really the first part, is this seeking behavior. Okay, the second part I want to get into is I want to get into the notion of a timer. So let's just label this seek. And I'm just going to hide the interface for the target vector. Okay, so now let's make a timer. This is where feedback, meaning previous frame, goes into the current frame. This is where feedback really comes to life. So I'm going to do a new VOP for this. And I'm going to call this timer. So let's dive in. Now, for this, we actually need, similar to the velocity coming in, doing something, going out to the velocity, we need to make an attribute, our own attribute, to represent the timer. So here, I'm going to start off using a parameter. I'm going to call this timer. And export when input is connected. That's really important, because we're going to be both reading it in and exporting it. I'm going to make it invisible. And that should be good for now. All right. And then I'm going to Control C, Control V. Now we have an identical parameter, and this is the one that's going to be reading it in. This is one that's going to be writing it out. And for that, we need to say, use this node to set parameter attributes. Okay, and now here is where the feedback loop is created. So now it's both reading it in and reading out. We could label that a bit, export timer and import timer. Okay, and then here's where the feedback comes in, is we're going to add. We're going to add a time increment each and every frame. Now let's see what happens. Let's go and get the timer. And notice in the first frame, it's already given us 1/24. So we go here, it's just increasing and increasing and increasing. Okay, well, that's cool. That really demonstrates feedback. But what kind of stuff can we do with this? Well, we haven't really made what I would call a timer yet, because the timer actually has a reset or a pulse that's associated with it. So I want this thing to reset every so often. So for that, I'm going to do a user interface parameter. We'll call this timer increment. All right, and let's say we want it to reset every 2 seconds. So I'm going to put a 2 there on the interface level. All right, so now as the timer is reading in, I'm going to compare it to the timer increment. I'm going to say if the timer is greater than or equal to, I guess, the timer increment, then I don't want you to export the timer. I want you to just reset. I want you to export a value of 0. So for that, we can use a two-way switch. We can say if that's true, then 0. Here we are. If it's false, then we're going to continue adding to the timer. So that's here. And this is going to be the timer that's exported. So now let's see what happens. It should be going up to 2, and then aha, so it resets. All right. So the timer divided by the timer increment, that has a lot of power inherent in it. So here we can use a divide. So here I'm just going to use the timer in another form here. Okay, and let's divide the timer and the timer increment. And at this point, we should be getting 0 to 1. And anyone that's been doing effects pretty long knows that 0 to 1 is powerful because you can use it for low versus high as opposed to 0 versus 1. So here it's going from black to white. And to get a better color preview going on, let's use a color mix. White on red seems to be pretty representative. Let's increase the timer a little bit. So let's maybe every third of a second. That's a little more exciting. Okay. Now, to get really creative with it, right now this is just a linear increasing. Well, let's actually put a ramp. And this is where the fuzzy logic is going to start. Because now we can remap these 0 to 1 or low to high values and make them progress along a range. Okay, so we'll call that curve. And let's say we just want to have more of an envelope. So it's going to be, like a shark swimming envelope. So it's going to be a thrust, and then it's going to die off. Musical notes are similar. Anytime something is impacting, it's also similar. Okay, so here I'm just kind of sculpting an attack envelope. See how it's got a quick impulse and then dies off very gradually. So you can see all the control we can have with something as simple as feedback. All right, so let's do one last little trick. Let's do a singular pulse. So this would be more of a animation cycle that would be triggering and looping through. I want to do a simple pulse. So for that, we would just do another compare, or we could simply say, is this value true or false? Okay, so if the timer increment is greater than that, let's just say pulse. So this is already a Boolean, it's an integer. So I'm just going to export this. There we go. So we have this pulse guy now, and every time it resets, you see how it's flashing 1 when it resets. And I just want to show you the application of these two concepts as they pertain as we dig a little deeper in the next lesson. So going over here, this is where I've done the pulse, and the pulse is responsible for the swimming as it seeks its prey. So I've got quite a few more curves in here, and it's all based on distance. So the farther away the shark is, the more pulses it's going to have, and it's going to swim faster because each pulse represents a swim. Okay, so here's the system we're going to go through, and just to premise it, we have to measure the relative distance, the distance of the target vector, the distance of the shark to its prey, and then measure that distance. We're going to set the speed that it needs to get to based on that distance. And then here, I've got a pulse timer, and it's going to reset every time, just like we've just performed. Okay. And eventually that will feed into adding to the velocity. So in comes the velocity, in comes our velocity, our direction. Basically, it's an envelope of the velocity going in that direction. It's going to export it. It's making sure it doesn't go too fast. So let's look at that as it happens. In the add to velocity, I've got a little diagnostic to help see that. Diag pulse vec. So viewing that, we can see what we're about to do. So we're going to combine the timer and the velocity, and each one of these pulses adds a vector and makes it seek its target differently. And that would be the most like swimming, most like swimming back and forth. See, if it's near its target, it's not adding as much to it. If it's far away from its target, it's going to accelerate toward its prey pretty quickly. Okay, so I hope you enjoyed the first introduction and really started thinking in terms of particles and feedback. In the next lesson, we're going to apply those concepts and make a pulse-based velocity system.